I know we've already talked a lot about resistance, and in this section, we're going to talk about those specific mechanisms of resistance that bacteria have. Resistance is a real issue, and I grabbed this picture just so that we can see how resistant organisms have become over the years. So, the first picture on the left, this is from 1991. And all of those little white dots, that's actually antibiotic. And when that antibiotic is applied to a lot of growth, when it kills the bacteria, we see a clearing. We call that clearing a zone of inhibition. So if you look at this clearing, and I'm just going to circle a clearing around one of those discs, you can see that the bacteria has been killed. So you can see in the first plate in 1991, there are several antibiotics that are doing a good job of actually killing the bacteria. You can see a couple on the plate where they are resistant. So I'm just kind of pointing those out. So you see no zone of inhibition, and you can see growth all over that disc. So that means that that organism is resistant. But most of those antibiotics in 1991 were doing a pretty good job of killing the bacteria. If you take a look at the picture from 2021, taking those same antibiotics, you can see that there's only a couple that actually worked where that bacteria was susceptible. So we know that resistance has increased over the years, and this is a big issue. And one of the things that we'll talk about is how is it that we can prevent resistance? So, resistance means that an organism that at one time was susceptible, that could be killed by that antibiotic, now that antibiotic no longer affects it. So, how does resistance actually happen? Well, through the previous chapters, we talked about increasing genetic diversity in bacterial populations. So, we talked about transformation and we talked about conjugation. So we know that genetic changes can occur by those bacteria acquiring those genes. So they can acquire resistance genes. So this allows resistance to antibiotics to spread through populations rather quickly. One of the ways that antibiotics can kill bacteria is to interfere with the making of their cell wall, that peptidoglycan. Sometimes bacteria can actually go into an L form. An L form is when they stop making a cell wall for several generations. So the antibiotics that are targeting that cell wall are not going to work because those bacteria are able to survive without that cell wall. We also know that some bacteria are very small, they can hide in cells, and they can also hide in tissues like tuberculosis in the lung. If we look at some other mechanisms of resistance, one of the ways that bacteria can develop resistance through alteration of targets. So, if let's say that we design an antibiotic to target a certain protein on that bacteria, if a mutation in the DNA happens to change that protein, now that antibiotic is no longer going to affect that protein. It's no longer going to be able to bind to it. So if mutations happen, now that antibiotic is going to be useless. Now we know that bacteria can reproduce very quickly, so mutations can happen very quickly. We also know that some antibiotics will work by targeting the bacterial membrane. So, if we develop an antibiotic that hits that membrane, if mutations happen where now those membrane proteins are not going to bind to those antibiotics and that antibiotic can't get through that membrane, now that bacteria is going to be resistant to that antibiotic. Some bacteria can actually develop enzymes that will break down the antibiotic. So, we talked about those beta lactam rings interfering with how the bacteria makes that peptidoglycan. Some bacteria can make beta lactamase. This is an enzyme that breaks down the beta lactam ring. So when they see that beta lactam ring, the enzyme gets to work and destroys it. We also know that bacteria can alter enzymes. So we talked about some of those inhibitors. So those anti-metabolites. So if we develop an antibiotic to affect an enzyme, but even when that antibiotic binds to it as an inhibitor, that enzyme is still able to work and that bacteria is able to continue with its metabolism. Now that bacteria can still make its energy source, so it's not going to be affected. If we develop an enzyme to target certain parts of a metabolic pathway, and that bacteria now has the ability to bypass that, then it's going to be able to live. So these bacteria can be very sneaky in evading these antibiotics. So for me, I have to draw things out. So I think it's a little easier to kind of see from a picture. So I've tried to draw each of these out. So the first one is the alteration of targets. So if we design a drug to bind to a protein, to bind to a receptor, if a mutation happens where now that antibiotic can no longer bind to it, now that antibiotic is not going to affect it. So you can see from my first picture on the left that antibiotic can bind to that receptor. But then in the second picture, because of a mutation, that receptor is changed. Now that antibiotic no longer binds to it. The second one, the middle picture, is alteration of membrane permeability. So if we design a drug and it can easily penetrate the membrane, it's going to harm that bacteria. But if that bacteria develops a way to stop that antibiotic from penetrating through the membrane, now that antibiotic is not going to be able to get through. It's not going to be able to cause harm. The beta lactamase. So you will see my beta lactamase on the bottom picture, kind of looks like a Pac-Man kind of looking figure. And then we have that beta lactam ring from those antibiotics like penicillin. That beta lactamase can gobble up that beta lactam ring, destroy it. So now it no longer impedes the development of that peptidoglycan synthesis. Alteration of enzymes. So there's my little Pac-Man enzyme at the top. If we design a drug to inhibit it, slow down that enzyme so that bacteria can't complete its metabolism, if it is able to still operate in the presence of that inhibitor, that enzyme still functions, it's not denatured, then that antibiotic really isn't going to do anything to that bacteria's metabolism. And then finally, alteration of metabolic pathway. So if you see on the left, A goes to B, goes to C, goes to D. So if this is the normal pathway of metabolism, if let's say that we design a drug to target B, so the intermediate B in this pathway, in order for the bacteria to get the product D that it needs for its metabolism, if we target B and we take B out, now it's not going to continue with its metabolism. However, if that bacteria now can find a way around having to go to intermediate B and it can bypass it and go from A to C, now it no longer needs B, so that antibiotic isn't going to do anything to it. So, a little bit more on resistance. If you go to the doctor and you are prescribed an antibiotic, this is usually what we call a first line drug. So, you go to the doctor for maybe a cellulitis or strep throat. They're going to prescribe an antibiotic. Hopefully, that first line drug, the first antibiotic that worked, actually does its job. If let's say that you start feeling a little better, and then after a couple of days, you're starting to feel bad again, now you're going to go back to the doctor and they're going to prescribe a second line drug. So that bacteria has become resistant. It's found that workaround. It's developed one of those mechanisms. So if you go back and you tell your clinician, this antibiotic is not working, I'm still not feeling great, they're not going to prescribe a drug that is going to work by a similar mechanism because we could have cross resistance. So if we prescribed another antibiotic that's going to have a beta lactam ring, but that bacteria has developed that enzyme, that beta lactamase, it's not really going to be helpful to add that antibiotic because it's not going to work. In fact, it could actually do more harm because it's going to continue to get rid of the good microflora that you have. So you certainly don't want to prescribe a second line drug that works by the same mechanism because that bacteria has already proven that it's got to work a way around that antibiotic, killing it. So, what can we actually do to limit drug resistance? So, first of all, when we're prescribed antibiotics, we should take that dose that should be high enough with that long course to actually kill all of the pathogens. So we want to make sure when we're prescribing as clinicians that we're prescribing a high enough dose and that we prescribe it for a long enough course to actually kill all of the pathogens and any of the mutants. The other thing that clinicians sometimes do is that they will actually add two antibiotics together. So they end up having a synergistic or an additive effect. So, for example, you might prescribe penicillin and streptomycin. So, penicillin can inhibit the cell walls because it has that beta lactam ring, and that's going to allow streptomycin in to do its job on the proteins as an aminoglycoside. Another drug that you've probably heard of is Augmentin. And Augmentin has amoxicillin, and it also has clavulanic acid. So if that bacteria has a beta lactamase enzyme to break down that beta lactam ring, the clavulanic acid actually ties up that enzyme and keeps it from inactivating amoxicillin so that it can actually get in and do its job. If you've ever had Augmentin or if you've ever given Augmentin to children, it doesn't taste as good as amoxicillin, but I can tell you from experience with my kids, it actually does a better job. At least it did for the infections that we had in our house. The other thing is that we want to restrict antibiotics for essential use. So if somebody has a flu virus, you don't want to prescribe an antibiotic because it's going to do more harm than good. Long gone are the days that you could call up the doctor and say, yeah, I think I've got a strep throat. Can you prescribe an antibiotic? They want to see you. They want to make sure that that antibiotic is necessary. So we don't want to overprescribe antibiotics. Of course, when they're necessary, we want to use them. So I mentioned making sure that we are using a high enough dose and taking our full medication. So every time that I'm on an antibiotic and I often forget to take a dose, my mind automatically goes to this picture. So this kind of takes us through a typical regimen of antibiotics and if we had an infection. So if you take a look at the top chart on day 0, this is basically a bell curve of the bacteria in our infection. So let's say that we have a strep throat infection. So here's the bell curve of the bacteria that's causing this infection. So on the one side, we've got our highly sensitive organisms. So as soon as we start taking that antibiotic, they're going to be knocked back. Then on the other side, we've got highly resistant organisms. It's going to take quite a bit to actually make a dent in that population. The majority of them are probably going to fall somewhere in between. So they're going to be intermediate. So we go to the doctor, we explain that we are not feeling well. Our clinician prescribes an antibiotic for us. So, as you know, in the beginning, we are good patients because we want to feel better. So, for the first few days, we're doing a good job. We're being the best patient and we're taking our antibiotics. So by about day 3, you'll notice that we've started to make a dent in those highly sensitive organisms and a pretty good dent in the intermediate organisms. You notice that we haven't really hit those highly resistant organisms. It's going to take a little longer to actually knock those back. But we're going to be good patients. So we're going to continue to take our antibiotic. And if you take a look at day 6, we've pretty much knocked back all of those highly sensitive organisms. We've made a really good dent in the intermediate organisms. And now we're finally starting to make a dent in our highly resistant organisms. It's probably at this point that we're probably feeling a little better. So we're probably getting more sleep. We're also eating better. So our immune system is also helping to knock this bacteria down. So we're very good patients. We take our antibiotic for the full 10-day course, and we've pretty much knocked back all of those pathogens. And now our immune system can kind of keep everything at bay, and we're feeling better. So this is if we're really good patients. Now, you know what happens. Life gets in the way, right? And sometimes we get forgetful, especially if we are starting to feel better. We think, well, it's okay if I miss a dose or two. So let's go back up to day 6. So day 6 is about we're really making a dent in this population. So we're starting to feel better. We're probably going about our daily activities. And so this is when we get forgetful. We're not taking our antibiotic. And we're like, yeah, you know what? I missed a few doses. I think I'm feeling better. I think I'm good. So if we stop taking our medicine for about 4 days, look at what happens at day 10. You notice that the population that has really taken off is our highly resistant organisms. So we have given them the chance to take off. And so now they are really abundant. And so now, if we start taking our antibiotic, now it's not going to work as well because of those highly resistant organisms. So now we're going to have to go back to the clinician and have them prescribe us a second line drug. The other problem with this is that as we're going about our business, we're feeling better, we're going back to work, we're going back to school. Now we're also spreading this resistant bacteria to everybody we know. And next thing you know, our family members are sick, or our friends, our coworkers are sick as well. So I always think of this picture every time I forget a dose. I don't want this to happen. And so if I forget a dose, I try to get right back on the good patient train and continue to take my antibiotics. The other thing that we should also not do is to take somebody else's antibiotic. We've all done it, but that puts us all at risk. So the person that should be taking it, they're not getting their full dose. And we're obviously not going to get the full dose as well. And that's probably going to set us all up for a second line drug. So the next time that hopefully you're not on an antibiotic anytime soon, but if you are, perhaps you will also be thinking of this picture as well. Since this is something that is so common and something that we definitely need to think about as far as resistance, spend a little time with this graph if it helps to kind of draw out the graph and explain what's happening. I think it can really help to kind of drive home that point.